Now students, let us discuss the hybridization involving d orbitals. Right, all of you? Hybridization involving d orbitals. Now what we have discussed till now, sp3, sp2 and sp hybridizations are over. Now let us discuss the hybridization involving d orbitals. In sp2, sp and sp3 no d orbitals are there. Now we discuss the d orbitals hybridization also. Now before going to discuss this one, now see here, 3d orbitals means which elements. Generally 3d orbitals are involved in hybridization. In the periodic table, elements present in which period participate or show this type of hybridization. Right? Generally 3s configuration, 3p configuration will be there. Clear? 3 indicates what? Period number. Whichever the elements present in third period or third period onwards, beyond third period, show this type of hybridization. That is d orbitals involving hybridization. sp3d, sp3d2 like this. sp3d3 we will discuss today. Clear? Now first of all you should remember which elements show this type of hybridization means elements present in the third period. Write down that point first, all of you. Elements present in third period onwards. Elements present in third period onwards show this type of hybridization. Show this type of hybridization. Sir, why sir? Some students will ask, why sir? Why not other elements, second period, first period elements, why not they show this type of hybridization means 1s only, first shell having only s orbital, second shell having only 2s and 2p orbitals. Clear? No 2d orbitals. D orbitals are present from third period onwards. 3d, 4d, 5d, 6d like this. Clear? Third period onwards d orbitals are present. Therefore, elements present in third period or beyond the third period always show this type of hybridization. Right? First part is clear, all of you. Now come to the second point here. 3d orbitals are there. Suppose here 3d orbitals are present in the third period. These 3d orbitals are having comparable energies. Comparable energy means what? Same energy, almost similar energy. 3d orbitals are having almost similar energy with 3s and 3p because they are also present in the same shell. 3d orbitals are also having similar energy with 3s and 3p orbitals. Clear? Now 3d orbitals are also having similar energy with 4s and 4p. With 4s and 4p orbitals, 3d orbitals also having similar energy. Now some students are thinking that, sir, it is present in third shell, all the 3 orbitals are present in the third shell, okay, they are having similar energy. We agree with your point. Now some students are thinking, here third shell, here fourth shell. Shell to shell some difference will be there, energy difference will be there. Right? Now, how they are almost similar energy? Because energy difference is not much between 3d and 4s orbitals. Remember, in d block elements, in most of the elements, electrons from 3d orbitals as well as 4s orbitals takes part in bond formation. This is very important, you should remember. When you enter into second year, then d block elements when topic is there you can understand very clearly. Electrons from 3d orbitals and 4s orbitals involved in bond formation. Why? Because of both same energy. Clear all of you? Means here question may be asked, among the following pairs of orbitals, intermixing of orbitals is possible. Clear? First one is 3s, 3b, 3d. Second option I will write 3d, 4s, 4p. Here intermixing is possible because all the orbitals are having similar energy. This is possible. Understood all of you? Now here, this is intermixing of atomic orbitals is possible or not? That is also important. No? This is also possible. Intermixing is possible because these two are having almost similar energy. Because of this reason, both the electrons from 3d as well as 4s orbitals involved in bond formation. Clear all of you students? Now I will write the second point here. 3s, 3p, 3d and 3d, 4s, 4p. Intermixing of orbitals. Intermixing of orbitals. Intermixing of orbitals is possible. Intermixing of orbitals is possible. Understood? Very important for your CET point of view also. Among the following set of orbitals, which orbitals undergo intermixing or which orbitals participate in hybridization? Important point you should remember. The next 3p and 3p orbital and 4s orbital. Both are having same energy or different energy. Energy difference is there or not? See here, 3p present in the third shell, 4s present in the fourth shell. Clear? There is a large energy difference between these two orbitals. Sir, here also same, no sir. Here also third shell, this is also fourth shell. How can you say here energy difference is less, here energy difference is more? Some students will think like this. Students, here electrons from 3d orbitals as well as 4s orbitals takes part in bond formation. When the electrons takes part in bond formation, they have almost similar energy. Clear? Now here 3p, here 4s. This is the third shell and this is the fourth shell. Energy difference is quite large. Such type of orbitals never participate in hybridization or never intermixing of orbitals is possible. This is also one more important point. We can write down 3p, 3d, or you can write first 3p and 4s. Between 3p and 4s, quite energy difference is there. Quite energy difference is there. Quite energy difference. Quite energy difference is there. Right? Between 3p orbital and 4s orbital, energy difference is there. We cannot intermixing such orbitals. Therefore, 3p, 3d, 4s, 3p, 3d, 4s. Such orbitals never intermixing. 3p, 3d, 4s. Understood? No intermixing of orbitals. No intermixing of orbitals. This is understood all of you. 3d orbitals are having comparable energies with 3s and 3p, and in the same way 4s and 4p. Therefore, these intermixing of orbitals is possible. Between 3p and 4s orbitals, energy difference is quite large. Such orbitals never participate or never intermixing of orbitals takes place. This is a combination. Here also possible question. Among the following pairs of orbitals, which pair does not involve in hybridization, or which pair intermixing of orbitals is not possible? 3p, 3d, 4s. This is not possible. Clear? Now first we will discuss the first type of hybridization here. sp3d hybridization. sp3d hybridization. sp3d hybridization means here one s orbital, 3 p orbitals, 1 d orbital. Write down here 1 s orbital, 1 s orbital, 3 p orbitals, 3 p orbitals, and 1 d orbital, 1 d orbital. 1 s orbital, 3 p orbitals, 1 d orbitals undergo mixing or intermixing to form 3 plus 1 4, 4 plus 1 5, 5 sp3d hybrid orbitals, hybrid orbitals like this. This is 1, this is 2, this is 3, this is 4, this is 5. 5 hybrid orbitals. All our hybrid orbitals are identical in all respects. Clear? Now I will write by taking one example. Will explain formation of PCl5. Formation of PCl5. Formation of PCl5. Right. Now which is central atom here? Phosphorus is the central atom. Ground state electronic configuration, ground state electronic configuration of phosphorus, ground state electronic configuration of phosphorus. Atomic number is 15, that is 1s2, 2s2, 2p6, 3s2, 3p3. Clear? Now valence shell is, this is the valence shell. Third shell is having 2 electrons. Third shell is having 3 electrons. 1, 2, 3. Understood all of you? Now here, according to hybridization, 1 s orbital, 3 p orbitals. Okay, where is the d orbital? D orbitals are not there here. Therefore, excited state is possible in this molecule. I will write the first excited state of, that is excited state. Excited state electronic configuration of phosphorus. 1s2, 2s2, 2p6, 3s2. Instead of 3s2, I will write the 3s1. 1 electron promotes from 3s to 3d orbital. Here 3d orbital 0. Vacant 3d orbitals are present in phosphorus because it is belongs to the third shell. 3s1, 3p3, 3d1. 3d1. I get the configuration here. 3s having 1 electron. This is related to, this is belongs to 3s. This is belongs to 3p. 1 electron, 2 electron, 3 electron. Now d orbitals are 5. D orbitals are 5 here. 1, 2, 3, 4, 5. D are having 1 electron. Clear? According to our hybridization, 1 3s orbital, 3 3p orbitals, and 1 3d orbitals undergo intermixing to form 1 plus 3 4, 4 plus 1 5, 5 sp3d hybrid orbitals. Write on the diagram for PCl5. So this is energy. First write the ground state. In a ground state, 3s2, 3p3. Ground state. Ground state. 3s having 2 electrons. 3p having 3 electrons. 1, 2, 3. Right? Here 3d. 3d. Why I am written like this? Slight energy difference will be there. Therefore 3s, 3p, 3d like this. Now here excitation of electron like this. Like this. One electron promotes from 3s orbital to 3d orbital. Excitation of electron. 3s having only one electron after excitation. 3s having only one electron. Then 3p as it is, no change. 3p having as it is, no change. Then 3d, one electron. 3d, one electron. Like this, one electron. This is the excited state. Now see here, in excited state, we can do like this. This is the excited state. Clear? Now come to the hybridized state. That is the hybridization. Now see one 3s orbital, 3p orbitals and one 3d orbital undergo or participate hybridization to form 5 sp3d hybrid orbitals. 5 like this. 1, 2, 3, 4, 5. All orbitals are having one electron each. 1, 2, 3, 4, 5. Here, this is I write 5 sp3d hybrid orbitals. Right. The remaining orbitals are vacant. That is the pure orbitals are no. You can write or may not write. It doesn't make anything difference because here anyhow they are vacant orbitals. If any electrons are present means then definitely we should write here. These are the pure orbitals. Here you can may write or may not write. See here. In case of hybrid orbitals, we cannot tell that this is a d orbital, this is a p orbital, and this is s orbital. All the orbitals are hybrid orbitals are similar only. They are having size, shape, energy, everything will be same. Therefore, in all you can say 5 sp3d hybrid orbitals are found. How to write the explanation? First write the ground state, excited state configuration, then write the diagram, then explain like this. After writing the diagram, you should write the explanation. Don't write directly that structure. We have to write the explanation by explaining all this diagram. The ground state electronic configuration of phosphorus is 3s2, that is the final is 3p3. Clear? 1s2, 2s2, 2p6, 3s2, 3p3. The excited state electronic configuration of phosphorus is 1s2, 2s2, 2p6, 3s1, 3p3, 3d1. Right? Now here, one 3s orbital, 3p orbitals, one 3d orbital undergo intermixing to form 5 sp3d hybrid orbitals, which are identical in all respects. These 5 sp3d hybrid orbitals are directed in a trigonal bipyramidal arrangement. Clear? Trigonal bipyramidal arrangement. I will write now here trigonal bipyramidal arrangement like this. 1, 2, 3. This is the trigonal bipyramidal. 1, 2, like this. This is a triangle. Like this. Trigonal bipyramidal arrangement. Right? Now I will explain. Out of 5 sp3d hybrid orbitals, 3 orbitals here. 3 orbitals of these 3 orbital hybrid orbitals are present in a triangle. The remaining 2 sp3d hybrid orbitals are present in the perpendicular to the equatorial bonds. Clear? Now see here, this is the plane. These 3 hybrid orbitals are present in the triangle. are present in the triangle. The remaining two sp3d hybrid orbitals are present, one above the plane, one below the plane. This is above the plane, this is below the plane. This is the plane, triangle. Three hybrid orbitals are present. One is above the plane, another one is below the plane. These hybrid orbitals are perpendicular to these triangle bonds. That is a triangle hybrid orbitals. Clear? Now see here. The 5 sp3d hybrid orbitals overlaps with chlorine. Now it should overlap with chlorine. I will write the chlorine configuration. Final configuration is 3s2 3p5. Valence shell electronic configuration of chlorine is 3s2 3p5. 3s having 2 electron, 3p having 5 electron. 1 2 3 4 5. Clear? Now one unpaired electron is present here. One unpaired electron is present in the valence shell. That is the last orbital. That electron is participate in the bond formation. This electron means phosphorus is having how many hybrid orbitals? 5. Clear? The 5 sp3d hybrid orbitals of phosphorus overlaps with pz, 3pz. pz orbital, z axis always involved in the sigma bond formation, because z axis is taken as the internuclear axis or molecular axis, right? The sp3d hybrid orbitals of phosphorus overlaps with the 3p orbitals of chlorine atom to form 5 phosphorus Cl sigma bonds like this. I will show one here. Cl means which orbital? This is a pz orbital. Pz orbital will be like this. Like this. Same orbital I will write here. One orbital, bond formation. Another orbital, bond formation. Another orbital, bond formation. Clear? Now here, 2 more are there. Same. P orbital. Both the lobes are same. See here. These are the hybrid orbitals. Hybrid orbital will be like this. Like this. This is a pure orbital. This is a pure orbital, not participating in hybridization. Hybrid orbitals of phosphorus atom overlaps with pz orbital of chlorine atom. There will be a formation of sigma bond between phosphorus and chlorine. Phosphorus and chlorine, sigma bond. Similarly, sigma bond formation like this. Here also sigma bond formation. Here, now same structure I will write like this. Here, triangle. 3 bond hybrid orbitals are present in the triangle. Now see here, like this. See here. Here one Cl bond, here one Cl bond. Here one Cl bond, here one Cl bond. These are the triangle. Now see here, like this. Now these are the perpendicular. 2 hybrid orbitals are present which are perpendicular to these triangular hybrid orbitals. Like this is the one hybrid bond, PCl bond. Here also PCl bond. Now see here, what is the bond angle between the hybrid? These are bonds will be present in the triangle. Now what is the these two or these two? These two. 120 degree. Bond angle is 120 degree. Now what is the bond angle? Now see, this is a triangle. This is a triangle. This bond is present above the plane, like this. Above the plane. This bond is present below the plane, like this. Means this bond is perpendicular to the bonds present in the triangle. Bonds present in the triangle. Means bond angle should be how much you are expecting? 90 degree. Here 90 degree. Bond angle is 90 degree. Now see here. These bonds are called as axial bonds. Very important this is structure. Axial bonds. This is also axial bond. These 3 bonds which are present in the triangle, that is called as equatorial bonds. Equatorial bonds. These are the axial bonds. These are the axial bonds. These are the equatorial bonds. Now clear here. Now come to the point here. Equatorial bonds. First I will explain this one. The three PCl bonds which are present in the triangle at an angle of 120 degree. At an angle of 120 degree. Clear? The two PCl bonds, that is axial bonds, which are present at an angle of 90 degree to the equatorial bonds. To the equatorial bonds. Clear? Now these bonds, axial bonds, are weaker bonds. This is the important point. You should remember. Axial bonds are weaker bonds. Why axial bonds are weaker bonds? This is the equatorial. Here axial means bond angle is how much? 90 degree. 90 degree means they experience repulsion. They experience repulsion means one repulsion, bond pair repulsion, bond pair repulsion, bond pair. Means one axial PCl bond experience three bond pair repulsions. 1, 2, 3. Similarly, the other which is present below the plane also experience bond pair repulsions. Therefore, when repulsions takes place, energy will be created. Energy will be created means bond angle, the molecule will be less stable, more reactive. Therefore, PCl5 is more reactive. Two types of bonds are present here. Therefore, what we have to do, what we learn according to hybridization concept here, bond angle, bond pair repulsion should be less. Bond pair repulsion should be less means these bonds should be made longer. These are the longer bonds. Equatorial bonds or axial bonds. Axial bonds are longer than equatorial bonds. Equatorial bonds. Longer bonds means, suppose this is a longer bond and this is a shorter bond. This is a longer bond, this is a shorter bond. Which is a stronger bond? Shorter bond is a stronger bond. Takes here. I cannot make it into two pieces very easily. But bigger bond, that is a longer chop piece, I can make two pieces very easily. Longer bonds are weaker bonds. Shorter bonds are stronger bonds. Therefore, here bond strength. One more important point here. Bond strength of axial bonds. I will write here. Axial bonds is weaker or less. Bond strength of axial bonds is less than equatorial bonds. All of you understood or not? These 2 points are very important. Why axial bonds are longer? First point, because axial bonds experience bond pair repulsion. To minimize the repulsion, axial bonds become longer. When axial bonds are longer, bond strength will be weaker. Bond strength of axial bonds are weaker compared to equatorial bonds. Any molecule in general possesses two types of bond angles. Such molecule is highly reactive, highly unstable. More reactive means unstable. These 2 points you can remember. Now students, next type of hybridization, write down sp3d2 hybridization. sp3d2 hybridization. PCl5 structure is very important. That is axial bonds, equatorial bonds. Please remember those 2 types of bonds. The next come to the sp3d2 hybridization. Here one s orbital, 3 p orbitals and 2 d orbitals intermixing to form 3, 4, 5 sp3d hybrid orbitals. Clear? 3, 4, 5, 6, no, not 5, 6 hybrid orbitals. Clear? Now let us take one example. Formation of sulfur hexafluoride SF6. Formation of formation of SF6. Now one more important point here, 3p orbitals. 3p orbitals means px, py, pz all are involved in hybridization, right? 2d orbitals. In previous one sp3d hybridization, there is one d orbital is involved in hybridization. Which d orbital is involved in hybridization? Question, very important question. In sp3d hybridization, which orbital is involved among the d orbitals? Their previous one. Just see the book. In sp3d hybridization, which d orbital is involved in hybridization? Write down there, all of you. There didn't written. dz square orbital. dz square orbital. Write down. dz square orbital is involved in sp3d hybridization. sp3d hybridization. Clear? Now here, in case of sp3d2 hybridization, which d orbitals are involved in hybridization? That is also question. Such questions will ask in the competitive exams. In sp3d2 hybridization, which d orbitals are involved in the formation of sigma bond? Sigma bond they will ask. Means hybrid orbitals always from the sigma bond. Means which orbitals are involved in hybridization, that we have to identify. Here 2d orbitals means dz square and dx square minus y square. dz square and dx square minus y square. These orbitals are involved in hybridization. Here, this is very important in competitive exam. You should remember what is dz square means. We will discuss the shapes. Electrons are present along the z-axis. Just remember, electron density, electron cloud, electrons all are same only. They are present along the z-axis. dx square minus y square is nothing but electrons are present along the x-axis, electrons are present along the y-axis. X-axis as well as the y-axis. Along the axis, square. Where is square present? Electrons are present along the axis. Logically you can remember. Clear? Now this is also very important, you should remember. Now you will write here ground state electronic configuration of sulfur. Ground state electronic configuration of sulfur. 1s2, 2s2, 2p6, 3s2, 3p3. This is the ground state. 3s having 2 electron, 3p having 3 electron. 1, 2, 3. 3p having 3 electrons. 3s having 2 electrons. Right? Now, according to our hybridization, 1s orbital, 3p orbitals. How many d orbitals? 2 d orbitals. D orbitals are not at all there. Therefore, here ground state sulfur 16 no, sodium, magnesium, aluminum, silicon, phosphorus, sulfur. 16 means you can write here 3p4. Phosphorus is 3s2, 3p3. Sulfur is 16, 3s2, 3p4. Means you can write one more electron here. Clear? Now 3d orbitals. You can write 3d orbitals. The 3d orbitals are 0. No electrons are present. Now we will promote one electron. First we have to promote the electron from 3p orbital to 3d orbital. First excited state. Electronic configuration of sulfur. 1s2, 2s2, 2p6, 3s2, 3p3, 3d1. Right? 3s having 2 electron, 3p having 3 electron, 3d having 1 electron. 3d having 1 electron. 1, 2, 3, 4, 5. Right? 2 d orbitals are equal here. Only 1 d orbital is present. Therefore, again one more excitation from 3s orbital to 3d orbital. Second excited state. Second excited state, electronic, you write down full electronic configuration of sulfur. 1s2, 2s2, 2p6, 3s1, 3p3, 3d2. 3s having 1 electron, 3s having 1 electron, 3p having 3 electron, 3p having 3 electron, 3d having again here 5 orbitals, 2 electrons, 1 s orbital, 3 p orbitals, 2 d orbitals participate in hybridization, sp3d2. Clear all of you? We cannot write directly second excited state. Step by step, we cannot remove 2 electrons at a time. Can you make 2 jumps in here at a time? Is it possible? Try at home whether it is possible or not. If it is possible, please inform me. I will also try. Okay? Now, see here. Diagram. Should write the diagram now. This is the configuration. Now, students, write the diagram here. This is the energy. What is the ground state? First, you can write the ground state. Ground state. In case of ground state, 3s to 3p4. 3s having 2 electron. 3p having 3 electron. 3p having 3 electron. Then 3d having 1, 2, 3, 4, 5. 2 electrons. 3d having 2 electrons. This is the ground state. Which excited state? First or second? Excitation. Second excited state. Second excited state of electron. Second excited state means here ground state means 3s2, 3p4. 3p4, right? In the ground state there is no electrons. 3d 0. 3d 0. See the just now written here 3s2, 3p4. 3s2, 3p4. Clear? Now second excited state. Second excited state means first excited state. I will do the first excited state. First excited state. 1 electron promotes from here to here. This is the first excited state. Second excited state. 1 electron promotes from here to here. 3s2, 3d orbital. Then you can write here 3s having 1 electron. 3p having 3 electrons. 1 electron is promoted here. 3 electron. Then 3d having 2 electrons. 1 electron is coming from 3p. 1 electron is coming from 3s. 2 electrons. This is the excited state. This is the excited state. You write down here excited state. Now come to the next, which one? Hybridized state. Hybridized state. I will write here hybridization. Hybridization. 1 3s orbital, 3p orbitals, 2 3d orbitals undergo intermixing to form 1 plus 3 4, 4 plus 2 6 hybrid orbitals. Hybrid orbitals are identical in all respects. We cannot differentiate like this. All the 6 will be equal energy like this. 1, 2, 3, 4, 5, 6. All are having 1 electron only. 1, 2, 3, 4, 5, 6. Right? I cannot say this is a d orbital, this is a s orbital, this is a p orbital. All are equal means 6 sp3d hybrid orbitals. Hybrid orbitals. This is a hybridized state. This is a hybridized state. Clear all of you? Now see here. Any orbitals are left over here, 3 orbitals are there, but they are not having any electrons. Means leave that one. Because if any electron is present here, then we have to write here. That is a pure orbital. What is a pure orbital? Not participate in hybridization. Here empty orbitals and vacant orbitals are present here. Therefore, if you write or may not write, it makes no difference. Clear? Now, after drawing this diagram, we have read the explanation. The ground state electronic configuration, you write first. The second excited state of electronic configuration, you can write this one. Then 1 3s, 3 3p, 2 3d orbitals intermixing or participate hybridization to form 6 sp3d hybrid orbitals which are directed octahedral arrangement. So see here octahedral arrangement. This is one hybrid orbital. Clear? This is another hybrid orbital. 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 Clear? What is the octahedral shape? These are the square. These 4 orbitals are present in the square. This is a square like this. This is one pyramidal, this is another pyramidal. Octahedral geometry also called as square bipyramidal geometry. Clear? Phosphorus having, sulfur having 1, 2, 3, 4, 5, 6 sp3d2 hybrid orbitals. Clear? Now, sulfur has to overlap with fluorine. What is the configuration of fluorine? 2s2, 2p5. 2s having 2 electron, 2p having 5 electron. 1, 2, 3, 4, 5. This orbital having 1 electron means sp3d2 hybrid orbital of sulfur overlaps with pz orbital of fluorine atom. Pz orbital of fluorine atom. What is the pz orbital? This is the pz orbital. This is the pz orbital. See here. One pz orbital. This is a sp3d2 hybrid orbital of sulfur overlaps with pz orbital of fluorine atom. There is a formation of sigma bond. Here also same. This is a pz orbital. There is a formation of sigma bond. Here also same like this. This is also pz orbital. You are thinking that this is one big, one small. This is both are big. No sir, means what is the difference? This is a pure orbital. This orbital not participate in hybridization. This is a hybrid orbital. What is hybrid orbital? Projection of orbital increases. Therefore, one lobe is bigger, another lobe is smaller. Such orbitals are called as hybrid orbitals. This is a pure orbital. This is the difference. We should identify. Now here also same. P orbital of fluorine atom. 6 fluorines are there. 6 pz orbitals. 1, 2, 3, 4. 2 more orbitals like this. 2 more orbitals. Here also 2 more orbitals. Right? Now see here. Sulfur is in the middle here. Sulfur. Here 1F. Sulfur fluorine bond. Here sulfur fluorine bond. Here sulfur fluorine bond. Sulfur fluorine bond. Here sulfur fluorine bond. Here also sulfur fluorine. Like this. Like this. Just to make a square for this one. Like this. Square bipyramidal or octahedral geometry. Octahedral geometry. What is the bond angle here? Bond angle is 90 degree. Bond angle is 90 degree. Any two bonds you can consider bond angle is 90 degree. This is the explanation you should write. sp3d, sp3d2 is already over. Now write down sp3d3 because just I'll explain the shape. No need to write all the explanation of this because it is not in your NCERT textbook. Just useful for a competitive exam. Which example, which d orbitals are involved, that you can write. sp3d3 hybridization. sp3d3 hybridization. Now see here, one s orbital, 3p orbitals, and 3 d orbitals. 3 plus 3 6, 6 plus 1 7. 7 new hybrid orbitals are formed. 7 sp3 d3 hybrid orbitals are formed. Right, these 7 sp3 d3 hybrid orbitals are directed pentagonal bipyramidal arrangement. Just energy diagram, all this is not required. Just remember the structure. That is example I will take here. IF7 iodine heptafluoride. Just remember IF7. Now here question arises. Which 3d orbitals are involved? One is dz square, another one is dx square minus y square, another one is any one dxy, dxz, dyz. xy or xz or yz. Among these three, any one participate in hybridization. This is fixed dz square, dx square minus y square. Among these three, any one orbital is involved here. I write the structure here. Iodine you can write here. Fluorine, 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 this is the pentagonal. This is a pentagonal. This is a pyramidal. This is a pyramidal. Pentagonal bipyramidal. Pentagonal bipyramidal. Pentagonal bipyramidal. Now what is the bond angle here? This is the axial bond. This is the axial bond. This is also axial bond. This is also axial bond. Here, now see here, what is the bond angle? Here 90 degree. Here or here you can take a 90 degree bond angle. Here in the pentagonal form, what is the bond angle? 72 degree. 72 degree. Bond angle is with axial bond 90 degree. Here among the pentagonal bonds 72 degree is the bond angle. Just to remember structure. Here in IF7, which d orbitals are involved and what is the type of hybridization present in IF7. Now let us discuss one question here. Let us discuss the one question. Write on the question, all of you. Write on the question. Chlorine atom. Chlorine atom. Chlorine atom in its third excited state. In its third excited state. In its third excited state, reacts with fluorine. Reacts with fluorine. Reacts with fluorine to form a compound. To form a compound X. To form a compound X. The formula and shape of X is. Question will be like this. Now what is the solution? First of all, you can write the chlorine ground state electronic configuration. Chlorine configuration 1s2, 2s2, 2p6, 3s2, 3p5. 3s having 2 electrons, 3p having 5 electrons. 3s having 2 electrons, 3p having 5 electrons. 1, 2, 3, 4, 5. Clear? What is mentioned in the question? Third excited state means first excited state, second excited state, third excited state. Like this, step by step you can do. First I will write the first excited state. First excited state. Configuration I will write. One electron promotes from 3p orbital to 3d orbital. I will write here 1s2, 2s2, 2p6, 3s2, 3p4, then 3d1. 3s having 2 electron, 3p having 4 no, 1, 2, 3, 4. 3d having 1 electron. Second excited state, according to question we have to follow. Second excited state. One more electron from 3p to 3d orbital. 1s2, 2s2, 2p6, 3s2, 3p3, 3d2. 3s having 2 electron, 3p having 3 electrons. Then 3d having 2 electron. Second excited state. Third excited state. Third excited state. Third excited state. One electron promotes from 3s orbital to 3d orbital. 1s2, 2s2, 2p6. Not required this. Just write down final valence shell electronic configuration. That is required. This is all time waste process. For your understanding, I am writing here. In the competitive exam, finally you can write 3s2, 3p5. That's all. Just follow this one because valence shell electrons are only involved in configuration. 3s1, 3p3, 3d3. 3s having 1 electron, 3p having 3 electron, 3d having 3 electron. 1, 2, 3. 3d having 3 electron. According to question, third excited state. Fluorine atom in third excited state reacts with fluorine. Reacts with fluorine. I will come to this side. See here. Reacts with fluorine. What is the fluorine configuration? 1s2, 2s2, 2p5. 2s having 2 electron, 2p having 1, 2, 3, 4, 5. Half filled orbital. Right? Orbital having 1 electron, that is unpaired electron. This orbital overlaps. Right? This orbital, 3s orbital overlaps with 2p orbital of fluorine. 3p orbital overlaps with like this. 2p orbital of like this 1, 2, 3, 4, 5, 6, 7. 7 orbitals, third excited state. These orbitals reacts with 2p orbital of 7 fluorine atoms to form bond formation between these two. Right? These 7 orbitals undergo intermixing now here. sp3, d3. Here these orbitals undergo hybridization. sp3, d3. Clear? How many are there? 7. 7 sp3, d3 hybrid orbitals reacts with 2p orbital of 7 fluorine atoms to form a pentagonal bipyramidal geometry. Formula should be like this. That is Cl1 like this. This is one more fluorine. Fluorine. Formula is Cl(F7). What is the shape? Formula is what? This is the formula. What is the shape of the molecule? Shape of the molecule is pentagonal bipyramidal. Pentagonal bipyramidal. Like these questions may be asked. Understood all of you? First you should write according to question. Third excited state. These orbitals undergo intermixing to form 7 sp3 d3 hybrid orbitals. These 7 sp3 d3 hybrid orbitals of fluorine overlap with 2p orbital of fluorine to form like this pentagonal bipyramidal molecule. Now students, how to calculate the hybridization? This question in any competitive exam you will get, right? Write a heading to predict the hybrid state of central atom, in covalent molecules or polyatomic ions. There are various methods are there. I will discuss all the three methods, but which one is easy for you? You can follow that one, right? Method 1. X equal to, what is x? X is nothing but number. If x is equal to 2, linear. If x is equal to 3, trigonal, planar. If x is equal to 4, tetrahedral, like this. X equal to half m plus v. Just remember, m plus v, where m equal to number of monovalent atoms for simple molecules. For simple molecule, this formula we have tried. M is equal to number of monovalent atoms attached to central atom. What is V? V is nothing but number of valence shell electrons on or of central atom. Clear? I will take one simple molecule, SF4. I will take one example. SF4 is a simple molecule. According to this, you will calculate X equal to number of monovalent atoms. Monovalent atoms means hydrogen and halogen, which can form only single bond. That is number of monovalent atoms attached to central atom. How much here? 4. X equal to half. Monovalent atoms are 4 plus. What is the V? V is nothing but valence shell electrons of central atom. How many valence electrons are having? Sulfur 6. Sulfur having 6 valence electrons. That is equals to half 4 plus 6 10. That is 2 ones are 2 5s are. Means you are getting 5. What is the hybridization? 3 4 5 sp3d hybridization. What is the shape here? Seesaw shape. Already we discussed here. Seesaw shape. Right? One lone pair will be there. Out of 6, 4 are involved. One lone pair will be present. Like this, we have to calculate. For simple molecules is over. For anions, X equal to half m plus v minus anion means negative charge. Negative charge is present means we have to add plus a for negative anions, right? For polyatomic, you can write polyatomic anions. This formula will be for polyatomic anions. Anion means what is A? Where A equal to magnitude of charge of anion. magnitude of charge on anion. Magnitude of charge on anion. I will take one example here. SO4 minus 2. Take example SO4 minus 2. You have to calculate the hybridization of sulfur. According to this formula, X equal to half. What is M? Monovalent atoms. Monovalent atoms are there here. Hydrogen and halogens are monovalent atoms. Monovalent atoms are not there. Monovalent atoms are not there means 0. Valence shell electrons. What is V? Number of valence shell electrons of central atom. How many valence shell electrons are present? 6. Valence shell electrons are 6. Right. One more is here. Anion plus A. What is the charge? Magnitude of charge on anion minus 2. If charge of anion, we should add. Negative means we should add plus 2. Like this, plus 2. That is equal to half. 6 plus 2, 8. That is equal to 4. 2 ones are 2, 4s are. 4 means X is equal to 4 means sp3. Understood all of you? Hybridization. Then polyatomic cations. We will discuss the polyatomic cations. X equal to half M plus V minus C for polyatomic cations. What is C? Magnitude of charge, where C equal to magnitude of charge on cation. Magnitude of charge on cation. Just example take here. H3O plus. According to formula, X equal to half. What is the monovalent atoms? Monovalent atoms are hydrogen. Hydrogen, halogen are monovalent atoms. Remember, hydrogen 3 are there, monovalent atoms. Oxygen having how many valence electrons? 6 valence electrons. 3, that is 2s2, 2p4. 6 valence electron. Right. Magnitude of charge. C is nothing but charge of a cation. How much charge is present? Magnitude 1. If a positive charge is present, we have to subtract minus 1. That is equal to half. 3 plus 6, 9. 9 minus 1, 8. That is equal to 4. 2 ones are 2 4s are. What is hybridization? sp3. sp3 hybridization. Like this, we have to calculate by using this formula. This is a method 1. Right? Other methods are there, we will discuss. Now students, second method, write down all of you. Method 2. Hybridization can also be predicted. Hybridization can also be predicted hybridization can also be predicted by steric number rule. Steric number rule. Steric number rule. Steric number equals to steric number equal to number of atoms attached to central atom. Number of atoms attached to central atom. Attached to central atom. Central atom plus number of lone pairs on central atom. Number of lone pairs. Number of lone pairs on central atom. On central atom. Clear? This is a second method. I will take one example here. Take an example here. xenon dioxy difluoride. Second example, BrF4 minus. We will discuss these two examples. Steric number equals to number of atoms. Central atom is xenon. Number of atoms attached to central atom: 2 oxygen atoms, 2 fluorine atoms. Total how many atoms are there? 4 atoms. 4 atoms attached to central atom. Number of lone pairs on central atom: xenon having 8 electrons in the valence shell. Out of 8 electrons, for one oxygen atom, double bond, 2 electrons gone. For second oxygen atom, double bond, 2 electrons gone. Clear? Now fluorine forms a single bond. For one fluorine, 1 electron. For another fluorine, 1 electron. How many number of lone pairs present on central atom? 2 lone pairs. Number of lone pairs present on, you can write, present on central atom. 2 lone pairs are present on central atom. That is 4 plus 2 how much? 6. 4 plus 2, 6. That is what is the hybridization? sp3d2, 3, 4, 5, 6. sp3d2 hybridization. Clear? Now second one take BrF4 minus. Steric number equal to, how many atoms are attached here? Mono atom, double atom, total atoms. See total atoms, 2 plus 2, 4 atoms. Lone pair means what? 2 electrons equals to 1 lone pair. Here, how many atoms are? 4 atoms. 4 atoms are attached to the central atom. Number of lone pairs present on central atom, if any, you can write in bracket. If any means if any lone pairs are present or not, that indicates. Bromine, 7 electrons, no? 7 electrons. 5 plus 2, 7 electrons. Out of 7, 4 electrons are involved in the bond formation with fluorine. 7 minus 4, 3. One negative charge is there. 4 electrons are present on bromine. Means how many lone pairs? 2 electrons, 1 lone pair. 4 electrons, 2 lone pair. 4 plus 2, 6. That is equal to 6. Understood? 4 plus 2, 6. sp3d2, 3, 4, 5, 6. Understood here? See once again. Number of atoms attached to central atom, that is 4 atoms are attached. Here the point is we have to find out the number of electrons, that is lone pairs present on central atom. Generally bromine having 7 valence electrons, 1 negative charge is there. Total 8 electrons are present. Out of 8 electrons, 4 electrons are involved in the bond formation. Then 4 electrons are present on the central atom. 4 electrons means 2 lone pairs. 4 plus 2, 6. 6 number means here you are getting 1 plus 3, 4. 4 plus 2, 6. sp3d2. This is the second method. Now come to the third method. Method 3. I will get the formula here. X equal to number of sigma bonds. Number of sigma bonds present around central atom. Around central atom plus number of sigma bonds present around central atom plus number of lone pairs on central atom present on central atom. If any, you can write in bracket. If any. Clear? Now we will take one example here. CO3 2 minus. Clear? How many sigma bonds are present around central atom? You should write first. You should know the structure. Otherwise, you can write carbon having how many valence electrons? carbon having how many valence electron? 4. We can write 4. 1, 2, 3, 4. 4 valence electron. How much negative charge? 2 negative charge. Negative charge means we have to add 2 electrons. You can add. Clear? Now this is over. Now 3 oxygen atoms. Oxygen always forms a double bond. 1 oxygen atom, 2 oxygen atom, 3 oxygen atom. Write down like this. Then according to formula, X equal to number of sigma bonds. Double bond. Double bond is nothing but one is sigma bond, another one is pi bond. Clear all of you? Sigma bonds only we have to consider. One sigma bond, two sigma bond, three sigma bond. Number of sigma bonds is 3 plus number of lone pairs. Any lone pairs are there here? No lone pairs. Therefore, 3 plus 0 that is equal to 3. 3 means sp2. Understood? 1, 2, 3. 3 plus 0 is 3. sp2 hybridization. 3 sigma trigonal planar arrangement. Last example we discuss. Take second one. Same SF4. Already solved. Discuss this one. Right? SF4. Sulfur. How many electrons? How many valence electrons here? 6. 1, 2, 3, 4, 5, 6 electrons. Fluorine always form single bond. 1, 2, 3, 4. Clear? Remaining electrons, whatever the remaining electrons, make pair. 2 electrons make one pair. 2 electrons make one pair. If any 2 electrons, another pair. If any 2 electrons, another pair. Right? According to formula, X equal to sigma bonds 1, 2, 3, 4. 4 sigma bonds. How many lone pairs? 1 lone pair. 4 plus 1, 5. 5 is nothing but sp3b hybridization. Understood? The last question we will discuss. Write on the question here. Among the following pairs, which one has same shape? Which one has same shape? Now write down the options, students. First option CF4 SF4. Second option BF3 PCl3. Third option xenon trifluoride carbon dioxide. Fourth option PF5 IF7. Such questions will ask in the competitive exam. Any competitive exam, among the following pairs, which one has identical shapes or same shape? You can write identical also. Identical shape. First one here, CF4. I will do here CF4 carbon. 1, 2, 3, 4. 4 electrons, 4 bonds. 1, 2, 3, 4. Right? 4 means 4 plus 0. 4 plus 0 means 4. 4 means sp3 hybridization. Here sp3 hybridization. Take SM4 sulfur. Sulfur having 6 electrons. 1, 2, 3, 4, 5, 6. 4 fluorine. 1, 2, 3, 4. Here one lone pair. 4 plus 1, 5. 5 means sp3d. Same shape means shapes should be same. Here sp3, here sp3d. They are not identical shapes. First option is incorrect one. Come to the second option. Boron. Boron having 3 valence electrons. 1, 2, 3. 3 fluorines. Single bonds. Fluorine, fluorine, fluorine. How many sigma bonds are there? This formula you can apply. 3 sigma bonds. 3 plus 0. 3 plus 0 is 3. 3 means sp2. Right. Here PCl3. Phosphorus. Phosphorus having 5 valence electrons. 1, 2, 3, 4, 5. Chlorine is 3. 1, 2, 3. 1 lone pair. 1 lone pair. Now see here 1, 2, 3. 3 sigma bonds, 1 lone pair. 3 plus 1, 4. 4 means here sp3. This is sp2 and this is sp3. This is also not correct. Now go to the third option. Third option I will do here. Third option, xenon difluoride. Xenon difluoride. Xenon is having 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. Fluorine. Here 1, here 1. Like this. 2 sigma bonds plus 3 lone pairs. That is equal to how much? 5. 5 is nothing but sp3d. What is the shape? When 2 sigma bonds are present, any number of lone pairs, shape will be linear. Remember. Now come to the CO2, carbon. Carbon having 4 valence electrons. 1, 2, 3, 4. Now any charge? No charge. 2 oxygens. Each oxygen bonded with a double bond. Each oxygen bonded with a double bond. Sigma bonds how much? 1, 2. 2 sigma bonds, 0 lone pairs. 2 sigma bonds. Means that is hybridization is sp. Even though hybridization is different here, but 2 sigma bonds are there, this compound is also having linear shape. Clear? This is your option. Correct option is this one. Don't think that hybridization should be same, then only you will get a same shape. See here 5. I will write the structure of this one. Xenon difluoride. Xenon. F. How many lone pairs? 3 lone pairs. Here 1 lone pair, 2 lone pair, 3 lone pair. Already we discussed trigonal bipyramidal geometry. If any lone pairs are present, that lone pairs occupy the equatorial position. This is the equatorial position. In deciding the shape of the molecule, lone pairs are not considered. We are considering the only bond pairs. What is the shape of the molecule? Linear shape. Therefore, linear. This is also linear. Your option will be this one. Here, 5 here. Phosphorus having 5 electron, 5 bonds, 5 plus 0, 5 means sp3d. Here, sp3d means trigonal bipyramidal. Iodine having 7 electrons. All the 7 electrons bond sigma bond with 7 fluorine atoms. 7 sigma bonds, 0 lone pairs. That is 7 means sp3d3. Pentagonal bipyramidal. Pentagonal bipyramidal, trigonal bipyramidal. Shape will be different. This is also not correct. Like this question will be asked. This is very important concept in any competitive exam. Now students, write down the today's assignment. First question. Explain the shape and hybridization of PCl5 by using sp3d hybridization. Right? Clearly we have to write first electronic configuration, then diagram, then write the explanation related to diagram, then finally write this is a hybridization and shape. What type of hybridization involved? What is the shape of the molecule? Second question. Explain the shape and hybridization of SF6 by using sp3d2 hybridization. This is also similarly we have to explain. Third one is additional. Such type of questions will be asked in the competitive exam. Right. Predict the type of hybridization in each of the following compounds. First one, CCl4. We have to identify the hybridization of central atom. Br at 5. They won't give any central atom. They will give the compound. We have to identify. Always central atom. Br at 5. NH4 plus nitrogen we have to identify. PCl3 identify the phosphorus hybridization. Okay.